Look up at the night sky, and for a moment, let your eyes linger on those distant pinpricks of light. They seem unchanging, eternal. But what if I told you the universe is far stranger, far more dynamic than our ancestors ever dreamed? Take the pillars of creation, those towering cosmic columns captured by the Hubble telescope. They're not just a stunning snapshot. They're a window into a reality where stars are born and die in explosions of unimaginable scale, where time and space bend in ways that defy logic. This is the universe as we're beginning to understand it, a place where every discovery peels back another layer of mystery, revealing questions we never even thought to ask. What if everything we've learned about space so far is just the tip of the cosmic iceberg? For centuries, humans have gazed at the heavens, weaving myths and mapping constellations, convinced we had the answers. But the deeper we look, the more we realize how little we truly know. Ancient astronomers charted the paths of planets without knowing what they were. Today, we're uncovering black holes that warp the fabric of reality itself. The journey from those early observations to our current cutting-edge discoveries is filled with moments that shattered our assumptions and redefined what's possible. And that's exactly what we're about to explore: 25 celestial wonders that didn't just change science. They transformed how we see our place in the cosmos. This isn't just a story of telescopes and equations. It's a saga of human curiosity, of relentless wonder pushing us to look further, dig deeper, and question everything. From the fiery deaths of massive stars to the eerie whispers of dark matter, each of these tales reveals a universe that's more bizarre, more beautiful, and more humbling than we ever imagined. So consider this your invitation to step beyond the familiar, to venture into the unknown, and to see the cosmos through eyes wide with awe. Because by the time we're done, you won't just know more about space, you'll feel it. In the vast cosmic tapestry of stars, one particular flickering light stands out as a true Enigma: KIC 8462852, better known as Tabby's star. Named after astronomer Tabby, who first spotted its bizarre behavior, this distant sun doesn't shine like any other. Instead, it dims unpredictably, sometimes by as much as 20%, as if something enormous is passing in front of it. At first, scientists thought it might be a swarm of comets or debris from a planetary collision, but the patterns didn't fit. The dips in brightness were too irregular, too dramatic. That's when the wilder theories began. Could this be evidence of an alien megastructure, like a Dyson sphere, built to harness the star's energy? Tabby herself put it best when she said, quote, "We'd never seen anything like this star." It was weird, and that weirdness forced astronomers to confront how much we still don't understand about stellar behavior. The light curves from Tabby's star don't match the smooth, predictable dimming caused by orbiting planets. Instead, they look like a chaotic scribble, as if the star itself is playing tricks on us. Even after years of study, no single explanation fully solves the puzzle. Some suggest it's vast clouds of dust, others propose a shattered moon's debris field, but the truth, we're still searching. What makes Tabby's star so compelling isn't just the mystery, it's how it reminds us that the universe thrives on the unexpected. Every time we think we've figured out the rules, nature throws us a curveball. And this star is just the beginning. Out there in the darkness, countless other celestial oddities are waiting to challenge what we think we know, each one a reminder that the cosmos is far stranger and far more wonderful than we ever imagined. Now picture this: our entire galactic neighborhood, including the Milky Way, is caught in a silent, unstoppable river flowing towards something we can't even see. This is the Great Attractor, a gravitational mystery so powerful it's pulling hundreds of thousands of galaxies toward a single point in space, like some cosmic magnet hidden behind a curtain. And here's the twist: we're part of that motion, racing toward it at over 2 million kilometers per hour, yet we've barely glimpsed what's pulling us. The reason: our own galaxy's thick band of dust and stars blocks the view, leaving this colossal force shrouded in secrecy. Astrophysicist René Cron-Courtoueg spent years painstakingly mapping this hidden region, using radio telescopes to peer through the Milky Way's veil. What she found was staggering: a sprawling cluster of galaxies, each adding to the gravitational tug, but still not enough to explain the full strength of the attractor. That's where dark matter enters the scene. Scientists suspect this invisible material, which makes up about 85% of the universe's mass, could be concentrating in this region, amplifying the pull. But even that theory leaves gaps. Some researchers speculate there's something even larger beyond it, a supercluster of galaxies so vast it redefines our understanding of cosmic structure. What's thrilling about the Great Attractor isn't just the mystery of its identity, but what it reveals about our place in the universe. We're not stationary observers, we're passengers on a galactic journey, caught in forces we're only beginning to measure. And just when we think we've mapped the cosmos, discoveries like this remind us how much lies beyond our sight, hidden in the darkness, shaping the universe in ways we're still struggling to comprehend. But if you think the Great Attractor is immense, wait until you hear about the next cosmic titan on our list, a structure so enormous it makes galaxies look like specks of dust. Imagine a patch of space so vast it could swallow thousands of Milky Ways whole, and yet it holds almost nothing at all. This is the Boötes Void, a cosmic desert stretching over 300 million light-years, where galaxies are so scarce you could cross its emptiness for lifetimes and see only darkness. To put that in perspective, if our solar system were a single grain of sand, the Boötes Void would be an empty football field with just a few scattered grains in the entire space. Most regions of the universe are woven into the cosmic web, a dense tapestry of galaxies clustered along invisible threads of dark matter. But here, the web frays into nothingness, as if someone carved a hole in the fabric of reality itself. Physicist Laura Mersini-Houghton once described voids like this as potential fingerprints of other universes, saying, quote, "What we perceive as emptiness might be the shadow of a neighboring cosmos brushing against our own." Her theory suggests that the Boötes Void could be a scar from the birth of the multiverse, a place where our universe's expansion collided with another's, leaving behind this eerie blankness. It's a haunting idea that what looks like absence might actually be evidence of something beyond our perception, but not everyone's convinced. Some researchers argue it's just a statistical fluke, a rare gap in the otherwise crowded cosmos. Others propose it's the work of forces we haven't discovered yet, perhaps even dark energies' influence sculpting space itself into these desolate pockets. What's undeniable is how the Boötes Void shatters our expectations. We're used to thinking of space as full of stars, planets, and swirling nebulae. But this void forces us to confront the unsettling truth that most of the universe isn't just unexplored. It's fundamentally empty, and if something this colossal can hide in plain sight, what else might we be missing? Now let's turn from this billion light-year silence to a mystery much closer to home. Right in our own solar system, there's a puzzle that's been baffling scientists for decades, one that might rewrite the story of our cosmic backyard. Deep in the frozen outskirts of our solar system, something massive is tugging at the fabric of reality, and we can't even see it. This is the mystery of Planet 9, a hypothetical giant world 10 times heavier than Earth, lurking so far from the Sun that a single orbit could take 20,000 years. The clues to its existence aren't in what we've found, but in what we can't explain: the strange, clustered paths of icy objects beyond Neptune that all tilt at the same angle, as if an invisible hand is herding them. Caltech astronomers Konstantin Batygin and Mike Brown first noticed this cosmic choreography back in 2016, calculating that the odds of such alignment happening by chance were less than 1 in 10,000. As Brown put it, quote, "We've only found the fingerprints of Planet 9 so far. The planet itself is still in shadow. The math behind this prediction is staggering." Imagine tossing a handful of rocks into the air and watching them arc in perfect unison. That's essentially what these distant objects like Sedna and 2012 VP113 are doing. Their elongated orbits point toward the same patch of sky, hinting at the gravitational pull of something enormous. But here's the catch: even our most powerful telescopes struggle to spot a cold, dark world that reflects almost no sunlight, especially when it could be 600 times farther from the Sun than Earth. Batygin compares the search to tracking a ghost, saying, quote, "It's like trying to find a black cat in a coal cellar with only a faint meow to guide you." Yet Planet 9's elusiveness might be more than just bad luck. Some theorists suggest its orbit could be tilted dramatically, throwing off our searches, or that it's not a planet at all, but a primordial black hole no wider than a grapefruit, warping space with the same gravitational force as a planet. Others wonder if we're seeing the echoes of a violent past, like a rogue world flung outward during the solar system's chaotic youth. Whatever the truth, this hunt forces us to confront how little we know about our own cosmic backyard. After all, if an entire planet can hide in plain sight, what other secrets might the outer solar system hold? And speaking of hidden forces, the next tale takes us even deeper into the unseen, where the fabric of reality itself bends to an influence far stranger than any planet. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: a reddish, cigar-shaped object moving too fast to be bound by the Sun's gravity. They named it Oumuamua, Hawaiian for scout or messenger from afar, and for good reason. This was the first confirmed visitor from another star system, a cosmic passerby with secrets we're still unraveling. At first glance, it seemed like a simple asteroid tumbling silently through the void. But then came the twist. Oumuamua wasn't just coasting, it was accelerating, as if pushed by some unseen force. Harvard astrophysicist Avi Loeb made headlines when he proposed a startling explanation that Oumuamua might be artificial, perhaps a light sail or debris from an alien civilization. The idea sparked fierce debate. Critics pointed to natural possibilities like outgassing hydrogen ice, which could explain the acceleration without invoking extraterrestrial engineering. But Loeb stood firm, arguing that Oumuamua's unusual shape, lack of a visible coma, and sudden speed boost set it apart from any known comet or asteroid. As he put it, quote, "When you hear hoofbeats, think horses, not zebras, but this wasn't a horse. It was something entirely new. What makes Oumuamua so fascinating isn't just the controversy, it's how it exposed gaps in our understanding." Traditional classification systems struggled to pin it down. Was it a comet without a tail, an asteroid with a hidden engine, or something else entirely? The closer we looked, the more it seemed to dance between categories, forcing scientists to reconsider the boundaries of what's possible. Even its origin remains a mystery. Some simulations suggest it could have been torn from a Pluto-like world in another star system, while others propose it's a fragment of a shattered planet. But if Oumuamua left us questioning the nature of interstellar objects, the next tale will challenge something far more fundamental. Because out there in the cosmos, there's a phenomenon so bizarre it seems to break the very laws of physics. A place where time, space, and reality itself twist into impossible shapes. Some of the most extreme objects in the universe don't just bend the rules, they shatter them completely. Take PSRJ 1748-2446 a neutron star spinning at over 700 times per second. At that speed, its surface moves at nearly a quarter the speed of light, defying what physicists once thought possible for such a dense object. Imagine a cosmic ballet dancer so massive that a single sugar cube-sized piece of it would weigh as much as Mount Everest, yet spinning so fast it could complete 3 full rotations in the time it takes you to blink. Nobel laureate Jocelyn Bell Burnell, who first discovered pulsars in 1967, described them as, quote, nature's most precise clocks, but even she couldn't have predicted how wild their variations would get. The physics behind these ultra-fast pulsars is mind-bending. Packed with the mass of a star crushed into a sphere no wider than Manhattan, their gravity warps space-time so severely that time itself slows down near their surfaces. Their magnetic fields, trillions of times stronger than Earth's, rip apart atoms and generate beams of radiation that sweep across the cosmos like lighthouse beams. But even these extreme objects have rivals: magnetars, neutron stars with magnetic fields 1,000 times stronger still. When a magnetar erupts, it releases more energy in a millisecond than our sun does in 100,000 years. In 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it briefly ionized Earth's upper atmosphere, proving these cosmic powerhouses could, in theory, fry electronics across the planet if one erupted nearby. Yet for all their ferocity, neutron stars also hold clues to one of the universe's greatest mysteries: time itself. Near these ultra-dense objects, gravity's grip is so intense that clocks would tick noticeably slower compared to those on Earth. It's a real-world example of Einstein's theory of relativity, where time becomes fluid, stretching and compressing based on gravity's pull. And if that's not strange enough, consider this. Some neutron stars exist in binary systems, orbiting so close to another star that they steal its matter, a process that can actually speed up their spin over millions of years. It's a cosmic feedback loop where gravity, time, and motion intertwine in ways that still baffle scientists. But if neutron stars challenge our understanding of physics, the next tale will take us even further into a realm where time doesn't just slow down. It stops altogether. Picture this: you're hurtling toward a black hole, watching the universe around you warp like a funhouse mirror as gravity's grip tightens. This isn't just science fiction, it's the mind-bending reality of time dilation, where the flow of time itself stretches and twists. Remember that iconic scene from Interstellar where 1 hour on the watery planet near Gargantua equals 7 years back on Earth? While Hollywood took creative liberties, the core idea is shockingly real. Near a black hole's event horizon, gravity is so intense that time slows to a crawl relative to the outside universe. It's as if the cosmos presses pause, but only for you. Scientists have actually observed this phenomenon in action around Sagittarius A, the supermassive black hole at our galaxy's center. Stars like S2 whip around it at blistering speeds, their orbits warped by spacetime's curvature. For every 16 Earth years S2 takes to complete one orbit, a clock near the black hole would tick just half as fast. That means an astronaut orbiting there would return to find everyone they knew aged twice as much. Einstein predicted this over a century ago with his theory of general relativity, proving gravity doesn't just pull, it bends time itself. Even our everyday tech relies on this truth. GPS satellites orbiting Earth experience time slightly faster than ground clocks, forcing engineers to account for microseconds of drift. Without these corrections, your phone's navigation would misplace you by miles within minutes. But here's where it gets even stranger. Light, the fastest thing in the universe, behaves paradoxically near these cosmic monsters. As photons struggle to escape a black hole's pull, they lose energy, stretching into longer, redder wavelengths, an effect called gravitational redshift. Yet from the photon's perspective, no time passes at all. It's a dizzying contradiction. Light, which defines the universe's speed limit, becomes frozen in time from its own frame of reference. This paradox hints at something profound, that at the edge of a black hole, the rules of physics as we know them might not just bend, but break entirely. And if that leaves your head spinning, just wait, because the next mystery we'll explore doesn't just warp time, it suggests entire dimensions might exist beyond the ones we perceive. For nearly a century, astronomers have calculated how fast the universe is expanding, a number called the Hubble constant. But here's the catch. Two of our most trusted measurement methods now disagree so sharply that scientists are calling it a crisis for cosmology. On one side, we have the Hubble Space Telescope, peering at pulsating stars and supernova in nearby galaxies. These observations suggest the universe expands at about 73 kilometers per second per megaparsec. On the other side, the Planck satellite mapped the afterglow of the Big Bang, the cosmic microwave background, and concluded the rate is just 67. That 6-kilometer gap might sound small, but after 13.8 billion years of cosmic expansion, it adds up to a glaring inconsistency. As astronomer Wendy Friedman put it, quote, "Either we're missing something fundamental in our measurements, or the universe is hiding new physics from us." What makes this tension so unsettling is that both methods are extraordinarily precise, like two world-class chefs using the same recipe but ending up with entirely different dishes. Hubble's approach relies on standard candles, celestial objects with known brightness to gauge distances. Planck's method traces the early universe's ripples, extrapolating forward using our best models of cosmic evolution. The fact that they disagree suggests one of three possibilities. Our measurements contain hidden errors, our understanding of dark energy is flawed, or something entirely unknown is tweaking the universe's expansion rate behind the scenes. Some theorists speculate that dark energy, the mysterious force accelerating cosmic expansion, might be changing over time. Others wonder if exotic particles or extra dimensions could be skewing the results. But the Hubble tension isn't just a niche academic debate. It's a crack in the foundation of modern cosmology. If our standard model of the universe can't explain this discrepancy, we might need to rewrite the textbooks. And while scientists scramble for answers, another set of cosmic oddities lurks in the background. Enormous structures so vast they defy the very principles of cosmic evolution. Stretched across the night sky like a bridge between worlds, the giant arc is a cosmic structure so vast it seems to defy the universe's own rules. Spanning an astonishing 3.3 billion light-years, this sprawling chain of galaxies shouldn't exist, at least not according to our long-held assumptions about how matter is distributed in the cosmos. The cosmological principle, a cornerstone of modern astronomy, states that on large enough scales, the universe should appear roughly uniform, like a well-mixed batter. But the giant arc, discovered by astronomer Alexia Lopez and her team in 2021, throws that idea into question. "When I first saw the data, I thought there must be a mistake," Lopez admitted. But the more we checked, the clearer it became. This structure is real, and it's rewriting what we thought we knew. What makes the giant arc so revolutionary isn't just its size, but its shape. Galaxies within it aren't randomly scattered. They're aligned along a near-perfect curve like beads on an invisible string. To grasp the scale, imagine a single light year as the length of a pencil. The giant arc would then stretch from Earth to the Moon and back over 100,000 times. Structures this colossal aren't just rare, they are theoretically impossible under current models of cosmic evolution, which predict a limit to how large matter can clump together. Yet there it is, a cosmic serpent slithering through the distant universe, composed of galaxies, galaxy clusters, and clouds of glowing gas, all bound by gravity's invisible threads. One tantalizing explanation is that our universe isn't as homogeneous as we believed. Instead, it might be fractal, a pattern repeating at every scale like a snowflake's branching arms. If true, this would upend centuries of astronomical thought, suggesting the cosmos organizes itself in ways far more complex than we've imagined. Lopez's team used light from quasars, the brilliant cores of distant galaxies, to map the arc's outline. As this light passed through clouds of magnesium gas, it left spectral fingerprints, revealing the structure's hidden skeleton. But the deeper mystery remains. What force could have sculpted something so immense? Dark matter's gravitational web might hold part of the answer, or perhaps we're seeing echoes of primordial fluctuations from the Big Bang itself, frozen in time. Yet for all its grandeur, the giant arc isn't alone. Other megastructures like the Sloan Great Wall and the South Pole Wall push similar boundaries, hinting that these cosmic titans might be more common than we ever suspected. Each one is a puzzle piece in a much larger picture, one where the universe isn't just expanding, but organizing itself in ways that challenge our very definitions of order and chaos. And if these structures force us to rethink the cosmos's architecture, just wait until you hear how the universe's most violent explosions are rewriting the story of how stars live and die. In the distant reaches of the cosmos, a dying star's final act is about to replay before our eyes not once, not twice, but 3 times. This is Supernova Requiem, a stellar explosion whose light has been fractured and twisted by the gravity of an intervening galaxy cluster, creating a cosmic mirage that defies ordinary perception. When Hubble first spotted this event in 2016, astronomers realized they were witnessing something unprecedented. The same supernova appearing in multiple places simultaneously, each image arriving at Earth by a different path through the warped fabric of spacetime. But the real revelation came when Steve Rodney's team calculated that one final, delayed image of the explosion would arrive in 2037, a prediction so precise it's like setting a celestial alarm clock for an event that happened 10 billion years ago. Gravitational lensing, the phenomenon behind this extraordinary light show, turns massive galaxy clusters into nature's telescopes. Just as a glass lens bends light to magnify distant objects, these clusters warp spacetime so severely that they distort and amplify the light from faraway supernova, quasars, and galaxies. Hubble's images of galaxy cluster MAX J0138 reveal this process in stunning detail, with stretched arcs of light Einstein rings, marking where background objects have been smeared into surreal shapes. But Supernova Requiem takes it further. Because the star's light traversed different paths around the cluster, each image represents a separate moment in the explosion's timeline, like watching a fireworks burst from multiple angles in slow motion. As Rodney explains, quote, "This isn't just a pretty illusion, it's a roadmap. The timing of each reappearance lets us measure the universe's expansion rate with unprecedented precision." What makes these lensed supernovas so valuable isn't just their rarity, it's what they reveal about the invisible scaffolding of the cosmos. By analyzing how the cluster's gravity distorts the light, scientists can map the distribution of dark matter, the mysterious substance that outweighs visible matter 5 to 1 yet emits no light of its own. The delayed arrival of Requiem's final image in 2037 will act like a cosmic scale, weighing the cluster's mass based on how long the light took to navigate spacetime's curves. Already, preliminary data hints at dark matter clumping in ways our models didn't predict, suggesting gaps in our understanding of how structure forms in the universe. Yet for all their brilliance, supernovae are fleeting candles compared to the ancient glow that permeates the cosmos, a relic so faint and pervasive it often goes unnoticed. This is the cosmic microwave background, the afterglow of the Big Bang, and buried within its whisper-thin signal are clues to even deeper mysteries. From the uneven distribution of its temperature fluctuations to the controversial cold spot that might hint at a collision with another universe, this primordial light is a palimpsest of the cosmos's earliest moments. And just as supernova Requiem's reappearance will shed light on dark matter, the next generation of telescopes probing this microwave haze may uncover truths about dark energy, inflation, and whether our universe is truly alone. But if ancient light holds answers about the universe's birth, then the next tale will take us even further back to a time before time, where reality itself flickered into existence from something smaller than a single atom. Embedded in the faint glow of the cosmic microwave background, the universe's oldest light lies a bizarre anomaly that shouldn't exist, the cold spot. Stretching nearly 2 billion light-years across, this region of space is significantly cooler than its surroundings, as if someone left a cosmic refrigerator door ajar in the aftermath of the Big Bang. At first glance, it might seem like a minor irregularity in the data, but this chill has sparked one of the most radical theories in modern cosmology, that our universe might have collided with another in its infancy, leaving behind a bruise in the fabric of reality. Theoretical physicist Laura Mersini-Houghton argues this could be the fingerprint of a parallel universe, a place where the laws of physics might operate entirely differently. As she describes it, quote, "The cold spot isn't just a statistical fluke, it's a wound, the place where our cosmos brushed against something outside itself." But not everyone's convinced. Skeptics point to a more mundane explanation: a supervoid, an enormous region of space unusually devoid of galaxies and matter. If such a void existed along our line of sight, light passing through it would lose energy, creating the illusion of a cold patch, a process called the integrated Sachs-Wolfe effect. The problem: no void large enough to explain the cold spot scale has ever been found. Astronomer István Shapudi led a team to map the region, only to discover that while there is a sparse area there, it's not nearly vast or empty enough to account for the temperature drop. It's like expecting a puddle to explain the depth of the Mariana Trench, he remarked. What makes this debate so electrifying is how it forces us to confront the limits of our cosmic maps. If the cold spot isn't a void and isn't noise in the data, then the multiverse theory gains startling credibility. Mersini-Houghton's models suggest that in the chaotic moments after the Big Bang, neighboring universes in the wider multiverse could have pressed against ours, leaving behind gravitational imprints. These collisions wouldn't just warp space-time, they might even seed structures like the cold spot, cosmic scars from a battle between realities. Yet the very idea of a multiverse remains contentious, partly because it's notoriously difficult to test. As philosopher of science Karl Popper once argued, a theory that can't be falsified isn't science, it's metaphysics. Amid this clash of ideas, one thing is certain: the cold spot refuses to fit neatly into any existing box. Whether it's proof of parallel worlds or a sign of physics we've yet to understand, it underscores how much of the universe remains uncharted. And if something this colossal can hide in plain sight, what else might be lurking in the cosmic shadows? Perhaps the answer lies not in the afterglow of creation, but in the wanderer's rogue objects adrift in the darkness, untethered from any star. Take, for instance, the enigmatic planet PSO J318.5-22. Discovered in 2013, this free-floating world drifts through interstellar space without a sun to warm it. At just 80 light-years away, it's shockingly young, a mere 12 million years old, and eerily isolated, glowing faintly with the residual heat of its formation. Most planets are bound to their stars, but rogues like this one are cosmic nomads, ejected from their birth systems by gravitational chaos. Astronomer Michael Liu, who led its discovery, calls them the universe's orphans, wandering the galaxy in perpetual night. What's fascinating about these rogue planets isn't just their loneliness, it's how common they might be. Some estimates suggest there could be billions in the Milky Way alone, outnumbering stars by as much as 20-1. Without a sun's glare to drown them out, they're nearly invisible, detectable only by the faint infrared warmth they emit or the way their gravity bends the light of distant stars. Yet their existence hints at a violent past. Simulations show that in a young solar system, gravitational tugs between giant planets can fling smaller worlds into the void, a process that might explain Earth's own water-rich composition if our planet's building blocks were hurled inward by such chaos. From the cold spot's cosmic conundrum to these wandering worlds, one theme emerges. The universe is far stranger, far more dynamic than we ever anticipated. And just when we think we've grasped its rules, it throws another curveball like the next tale we'll explore, where time itself seems to run backward in certain corners of the cosmos. Hubble's sharp eyes once caught something utterly bizarre, a supermassive black hole, weighing as much as 20 million suns, barreling through space so fast it left a 200,000 light-year-long trail of newborn stars in its wake. This isn't science fiction. It's the aftermath of a cosmic collision so violent it sent a black hole hurtling like a cannonball. Astronomer Pieter van Dokkum described it as a runaway monster, plowing through the gas of the cosmos and igniting fireworks wherever it goes. Normally, black holes sit motionless at the hearts of galaxies, but when two galaxies merge, their central black holes can spiral inward, locked in a gravitational dance. If one gets kicked outward by the immense forces, a phenomenon called a recoil event, it becomes a cosmic fugitive, streaking through intergalactic space at speeds up to 4 million miles per hour. What makes this discovery so extraordinary isn't just the black hole's speed, it's the unexpected stellar nursery it left behind. As the black hole raced outward, its gravity compressed the gas in its path, triggering star formation like a celestial breadcrumb trail. Van Dokkum's team compared it to a bulldozer plowing through snow, leaving ridges in its wake. These aren't just any stars, they're young, blue, and fiercely luminous, clumped in tight knots along the black hole's path. It's a paradox, a destructive force of nature inadvertently creating new life, proving once again that the universe thrives on contradiction. Yet for all its drama, this runaway black hole might not be alone. Hidden in the Milky Way's outskirts, astronomers suspect there are nomadic black holes, stellar mass remnants of ancient star clusters or shattered dwarf galaxies, drifting unseen through the darkness. Unlike their supermassive counterparts, these loners don't announce themselves with glowing accretion disks or starry trails. Instead, they betray their presence only when their gravity bends the light of a background star, a fleeting distortion called microlensing. Some estimates suggest our galaxy could host as many as 100 million of these dark wanderers, each a ghostly reminder of the chaos lurking in what seems like empty space. But if a black hole racing across the cosmos bends your mind, just wait until you hear about a place where the laws of physics seem to run backward. a realm where entropy decreases, time stutters, and reality itself unravels. Across the observable universe, hundreds of galaxy clusters are caught in a current they can't resist, streaming toward something so distant, so massive, that it lies beyond the edge of everything we can see. Astronomers call this phenomenon dark flow, and it's as unsettling as it sounds. Imagine tossing a handful of leaves into a river, only to watch them all drift stubbornly in one direction, defying the wind and the current. That's precisely what's happening here, except the river is space-time itself, and the leaves are entire galaxies hurtling toward an unseen horizon. Alexander Kashlinsky's team first detected this motion in 2008, using the cosmic microwave background as a reference frame. By tracking how galaxy clusters scattered this ancient light, they found something impossible to ignore: a collective movement toward a patch of sky near the constellations Centaurus and Vela, as if the universe itself were tipping toward some colossal, hidden mass. The implications are staggering. For dark flow to exist, whatever's pulling these galaxies must lie beyond the cosmic horizon, the 14 billion light-year limit of what we can observe. That suggests one of two possibilities. Either our universe is far larger than we thought, with structures extending into regions we'll never see, or something even more radical is at play. Kashlinsky himself leans toward the latter, proposing that this motion might be the gravitational tug of another universe, a neighboring bubble in the multiverse pressing against our own. It's like standing on a shore and feeling the tide pull at your feet, he explains, even though the ocean stretching beyond the horizon is invisible to you. Critics argue that statistical errors or unknown local effects could mimic the signal, but the persistence of dark flow across multiple studies keeps the mystery alive. What makes dark flow so electrifying isn't just the scale, it's the way it upends our cosmic complacency. We're used to thinking of the observable universe as the ultimate frontier, but this phenomenon hints at realms beyond, where the rules of physics might be unrecognizable. And if gravity can reach across the void between universes, what other forces might be leaking through? The answer could rewrite not just cosmology, but our very understanding of reality. Yet for all its grandeur, dark flow isn't the only enigma-defying explanation. While some cosmic mysteries involve unseen forces pulling matter, others involve matter itself vanishing without a trace. Take the case of the missing stars. In 1952, astronomers catalogued 3 bright objects in a single photographic plate of the constellation Lupus. By 2016, when researchers revisited the same patch of sky, all 3 had disappeared. No supernova, no black hole, not even a fading ember, just empty space where stars once blazed. These weren't the only vanishings. Over the past century, at least 100 similar disappearances have been recorded, with no satisfying explanation. One theory suggests failed supernova, where massive stars collapse directly into black holes without the usual explosive fanfare. Another proposes primordial black holes, ancient relics from the Big Bang, passing in front of stars and lensing their light into invisibility. But the most tantalizing idea, rogue black holes or neutron stars cloaked in thick dust clouds, drifting between us and the stars like cosmic thieves snuffing out streetlights. The unsettling truth is this: for all our telescopes and technology, the universe still holds cards it hasn't revealed. Whether it's galaxies tugged by invisible hands or stars winking out of existence, each mystery is a reminder we're not just observers of the cosmos. We're detectives piecing together a puzzle where the pieces keep changing shape. And just when we think we've grasped the pattern, the universe throws us another curveball, like the next tale we'll explore, where time itself seems to stutter and reverse in certain corners of the cosmos. Somewhere in the vast archives of astronomy, hidden among glass plates and digital sky surveys, lies evidence of stars that simply vanished. No explosion, no fading embers, just an empty patch of sky where a pinpoint of light once burned. The Vanishing and Appearing Sources during a Century of Observations project, or VASCO, has scoured historical records to catalogue these cosmic disappearing acts, uncovering over 100 cases where stars present in mid-century photographs are nowhere to be found in modern images. Astrophysicist Beatriz Villarroel, who leads the initiative, describes the search as a cosmic detective story where the evidence keeps evaporating before our eyes. One of the most baffling cases involves a trio of stars in the constellation Lupus, all visible in a 1952 plate from the Palomar Observatory. By 2016, not a single trace remained. The leading theory suggests these might have been failed supernova massive stars that collapsed directly into black holes without the usual brilliant finale. When a star's core implodes under its own weight, it can sometimes skip the explosive stage entirely, vanishing like a candle snuffed out under a glass. But there's a catch. Even failed supernova should leave behind a telltale infrared glow as dust absorbs the dying star's heat. Yet in many cases, including the Lupus trio, follow-up observations found nothing. No dust, no remnants, just silence. This absence opens the door to wilder possibilities. Could some of these vanishings be signs of alien megastructures, like hypothetical Dyson spheres designed to harness a star's energy? The idea isn't as far-fetched as it sounds. Villarroel's team has specifically searched for stars that dim or disappear abruptly, potential hallmarks of artificial engineering. While no conclusive evidence supports this theory, the mere fact that scientists are seriously considering it speaks volumes about how little we understand these phenomena. As Villarroel notes, when nature refuses to follow the scripts we've written, we have to ask, are we missing something obvious, or is the universe playing by rules we haven't discovered yet? Yet the greatest enigma might not lie in distant galaxies, but much closer to home. Buried in the Milky Way's own history are gaps that hint at cataclysmic events we're only beginning to piece together. Geological records on Earth show sudden spikes in radioactive isotopes like iron-60, traces of nearby supernova that might have bathed our planet in radiation multiple times over the past 10 million years. Some researchers speculate these explosions could have triggered mass extinctions or even influenced human evolution. But here's the twist: when astronomers search for the remnants of those supernova in our galactic neighborhood, they find far fewer than expected. It's as if the Milky Way has been selectively erasing its own past, leaving behind only cryptic clues in the form of ghostly gamma-ray bubbles and oddly distributed stellar corpses. What connects these modern vanishings to our galaxy's forgotten cataclysms is the unsettling realization that the cosmos is far more dynamic and far more destructive than our telescopes can capture. Stars don't just fade gently into the night. They can be ripped apart by black holes ejected from galaxies or even swallowed whole by cosmic voids. And if entire stellar disappearances can go unexplained, what else might we be missing? The answer could rewrite not just our understanding of stellar life cycles, but the very story of our place in the universe. Now consider this: while we've been searching the skies for vanishing stars, an even stranger phenomenon has been hiding in plain sight, one where the laws of physics seem to unravel and time itself might flow backward. Our galaxy's closest neighbor, Andromeda, hides a violent secret in its starry depths, evidence of a cosmic feast that reshaped its history. Thanks to the European Space Agency's Gaia telescope, astronomers like Dougal Mackie have uncovered something astonishing. Andromeda didn't always stand alone. Billions of years ago, it devoured a massive sibling galaxy in what's now called the last major merger. The clues, strange streams of stars orbiting against Andromeda's rotation, like cosmic breadcrumbs leading back to a forgotten collision. These stellar rivers, rich in metals and moving in tight, looping paths, don't match the galaxy's natural motion. Instead, they're the shredded remains of a once proud galaxy torn apart by gravity's relentless pull. Mackey's team traced these orphan stars using Gaia's precision maps, revealing how the merger unfolded. As the victim galaxy spiraled into Andromeda, its outer stars were flung into chaotic orbits, while its core was digested slowly, a process that might have sparked waves of star formation visible today. The scale of this event is staggering. The devoured galaxy was no minor snack. It was a titan roughly a quarter of Andromeda's size, making this one of the largest galactic mergers ever detected in our cosmic neighborhood. It's like finding fossilized footprints of a dinosaur long after it's vanished, Mackey explains. The stars remember, but this ancient clash isn't just a relic, it's a preview. In about 4 billion years, the Milky Way and Andromeda will collide in a similar dance, their stars weaving new patterns across the sky. The difference. This time we'll have front row seats. Simulations show that when galaxies merge, their stars rarely collide. Space is too vast, but their gravitational tides can fling planets from their orbits, scramble solar systems, and ignite bursts of stellar birth. Imagine the night sky filled with strange constellations as alien suns join our own, their gravity-tugging comets loose from the Oort cloud, sending icy projectiles hurtling inward. What's truly humbling is how these mergers rewrite galactic histories. Andromeda's cannibalized sibling was likely a builder, contributing stars, gas, and even dark matter to its larger neighbor. In a sense, galaxies grow not just by accumulating dust, but by absorbing entire worlds. And if Andromeda's past is this violent, what other secrets might the Milky Way be hiding? Recent studies suggest our own galaxy's halo contains the mangled remains of at least 6 smaller galaxies, their stars orbiting like ghosts in the cosmic dark. Yet for all their destructive power, these mergers are also creators. The shockwaves from colliding gas clouds trigger star formation, while the mixing of elements from different galaxies seeds new planets. It's a reminder that even in the chaos of the cosmos, destruction and creation are two sides of the same coin. And as we piece together these celestial puzzles, we're not just uncovering the past, we're glimpsing the future of our own galactic home. Now consider this: if galactic mergers can reshape entire star systems, what happens when something even more powerful takes the stage? A force so intense it can rewrite the laws of physics in its wake. 4 billion years ago, our solar system wasn't the orderly neighborhood we know today. It was a cosmic battlefield. This was the era of the late heavy bombardment, a time when asteroids the size of cities rained down on planets in a cataclysmic storm that reshaped worlds. The evidence is etched into the moon's scarred face, where ancient craters like Tycho and Copernicus stand as silent witnesses to this violent chapter. But what triggered this chaos? The answer lies in a gravitational dance among the gas giants, a celestial shuffle that sent shockwaves through the entire system. Astronomers call it the Nice Model, named not for its pleasantness but for the French city where it was developed. Here's how it unfolded. Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. Instead, they lurked closer together in the early solar system, locked in an unstable embrace. As Jupiter and Saturn's orbits synchronized, a process called orbital resonance, their combined gravity flung Uranus and Neptune outward like cosmic pinballs. The resulting gravitational upheaval destabilized the asteroid belt, hurling countless rocks inward toward the inner planets. The scars of this onslaught are everywhere: Mercury's battered surface, Mars's pockmarked highlands, and Earth's own lost geological records, erased by eons of erosion. Even the Moon's magma oceans, sampled by Apollo astronauts, contain isotopes matching asteroids from this era, smoking gun evidence of a system-wide catastrophe. But the late heavy bombardment wasn't just destruction. It was also a delivery service. Many of those incoming asteroids carried water and organic molecules, the raw ingredients for life. Without this violent reshuffling, Earth might have remained a dry, barren rock. The gas giant's migration acted as a cosmic reset button, scattering materials that would later become the building blocks of oceans and atmospheres. As planetary scientist Sean Raymond puts it, the solar system's teenage rebellion was messy, but it set the table for life's eventual feast. Yet for all its fury, this bombardment pales next to the mysteries lurking in today's outer solar system. Beyond Neptune, where the sun's light is a faint whisper, objects like dwarf planet Haumea spin at breakneck speeds, while others orbit at bizarre tilts. Hints of ancient collisions or gravitational encounters we're only beginning to unravel. These oddballs refuse to fit the neat patterns we've come to expect, suggesting that the solar system's adolescence was even wilder than we've dared to imagine. And if our own cosmic backyard holds such surprises, just wait until you hear what happens when entire planets defy the laws of physics, turning our understanding of planetary formation upside down. Imagine a world where the ground beneath your feet isn't rock or sand but glittering diamond. This isn't science fiction. It's the reality of 55 Cancri, a planet twice Earth's size orbiting so close to its star that a single year lasts just 18 hours. Discovered in 2004, this scorching world defies every expectation. Yale astrophysicist Niku Madhusudhan and his team analyzed its composition, revealing something extraordinary. Up to a third of the planet's mass could be crystallized carbon diamond. As Madhusudhan puts it, quote, "This isn't just a planet, it's a jewel floating in space, forged in conditions we can barely comprehend. The extremes don't stop there." 55 Cancri's surface temperatures soar above 2,000 degrees Celsius, hot enough to melt steel. Its parent star bathes it in relentless radiation, stripping away any atmosphere it might once have had. Yet beneath this inferno, pressures are so intense that carbon atoms lock into diamond's crystalline structure, creating a mantle that might gleam like a cosmic treasure chest. To grasp how alien this is, picture Earth's carbon-rich crust, our coal, our oil, our graphite. Now compress it under unimaginable heat and pressure until every atom rearranges into the hardest natural substance known. That's 55 Cancri, a world where the very soil is precious beyond measure. But how does such a planet form? The leading theory involves a catastrophic chemical imbalance. Most rocky planets, like Earth, form from silicon-rich material. But if a protoplanetary disk contains far more carbon than oxygen, a rare but possible scenario, carbon compounds dominate. In this environment, carbon bonds with itself instead of oxygen, creating carbides that, under heat and pressure, crystallize into diamond. Some astronomers speculate 55 Cancri might be the remnant core of a gas giant whose atmosphere was ripped away, leaving behind a carbon-rich skeleton. Others suggest it's the product of a stellar system born in a molecular cloud unusually rich in carbon, a cosmic quirk that shaped its destiny. What's truly fascinating is what this diamond world reveals about cosmic chemistry. Carbon, the backbone of life on Earth, becomes something entirely different under extreme conditions. On 55 Cancri, it's not the building block of DNA, it's the foundation of continents. This duality forces us to rethink how elements behave across the universe. Carbon might create life here, but elsewhere it crafts landscapes of glittering stone. And if diamonds can form entire planets, what other exotic worlds might be out there? Silicon carbide spheres, metallic hydrogen oceans. The possibilities stretch as far as the periodic table itself. Yet for all its allure, 55 Cancri E is just one thread in a much larger tapestry. Across the galaxy, elements combine in ways that challenge our Earth-centric assumptions, crafting worlds where chemistry follows rules we're only beginning to decode. Each discovery peels back another layer, revealing a universe far stranger and far more diverse than we ever dreamed. And as we turn our gaze to the next celestial wonder, consider this. If carbon can build diamonds the size of planets, what other treasures might the cosmos be hiding? Deep in the heart of the Milky Way, near the constellation Sagittarius, floats a cloud so vast it could fill a trillion wine glasses, and it's 10,000 times stronger than anything you'd find on Earth. This is Sagittarius B2, a cosmic cocktail of ethyl alcohol, methanol, and other complex organic molecules stretching over 400 light-years. Astrochemist Rob Garrod describes it as nature's ultimate distillery, where temperatures near absolute zero turn gas and dust into sprawling molecular factories. Within this frigid brew, chemical reactions build the precursors to life itself: amino acids, sugars, even the building blocks of DNA. And here's the twist. While the cloud's alcohol content alone could intoxicate every human on Earth billions of times over, its real significance lies in what these molecules reveal about the universe's hidden creativity. Garrod's simulations show how these molecular clouds act as cosmic kitchens. Under the harsh radiation of nearby stars, simple compounds like carbon monoxide and water ice cling to dust grains, forming icy mantles. Over millennia, radiation breaks and reshapes these molecules into ever more complex structures. Some eventually detach, floating free as organic snowflakes in the void. It's a process that could be happening right now in thousands of similar clouds across the galaxy, quietly assembling the ingredients for life long before planets form. We used to think life's building blocks were rare, Garrod explains. Now we know the universe is practically marinated in them. But Sagittarius B2 isn't just a passive ingredient dump. Its molecules emit distinct radio signatures, allowing astronomers to map their distribution like a celestial bartender taking inventory. The result: a staggering diversity: vinyl alcohol, ethylene glycol, even the sweet-smelling ester ethyl formate, the same compound that gives raspberries their aroma. Finding these in space suggests that the chemistry we associate with life isn't just an earthly fluke. It's woven into the fabric of the cosmos. Yet for all its abundance, this alcoholic nebula pales next to an even stranger phenomenon, one where space doesn't just host life's ingredients, but seems to mimic life itself. In the Orion Nebula, vast plumes of gas twist into shapes eerily reminiscent of DNA's double helix, while elsewhere, star-forming regions pulse with rhythmic jets of material like cosmic heartbeats. These aren't signs of actual biology, of course, but they blur the line between chemistry and something far more mysterious. As astronomer Carl Sagan once mused, the universe seems neither benign nor hostile, merely indifferent, but sometimes it winks. What makes these molecular clouds and their lifelike patterns so profound is how they force us to redefine life. If the raw materials for biology are universal and nature keeps sculpting them into familiar forms, does that mean life is an inevitable outcome or just a happy accident? The answer might lie not in distant galaxies, but closer to home, where another cosmic oddity is rewriting the rules of existence. The universe teems with hundreds of billions of galaxies, each brimming with stars, so where is everybody? This is the Fermi Paradox in its starkest form, the unsettling contradiction between the high probability of extraterrestrial civilizations and the deafening silence we've encountered so far. Astronomer Jill Tarter, who dedicated her career to the search for extraterrestrial intelligence at SETI, offers a humbling perspective. Absence of evidence isn't evidence of absence. Our radio telescopes have scanned less than a fraction of a percent of the cosmic ocean, and even then, we might be listening for the wrong signals. Imagine ants trying to detect Wi-Fi. That's how mismatched our technology could be with an advanced civilization's communication methods. But what if the silence isn't accidental? Enter the dark forest hypothesis, a chilling answer to the paradox inspired by the works of sci-fi author Liu Cixin. Picture the cosmos as a vast, shadowy woodland where every civilization is a hunter, terrified of revealing its location. In this scenario, any species that broadcasts its presence risks annihilation by a more advanced and paranoid neighbor. The logic is grimly persuasive. In a universe where resources are finite and trust is non-existent, preemptive strikes become the only survival strategy. If true, it would explain why our calls into the void go unanswered. The galaxies might be crowded, but everyone is holding their breath, yet not all explanations are so bleak. Some scientists propose we're simply too early or too late. The universe has been habitable for billions of years, but the window for technological civilizations to overlap might be vanishingly small. Others suggest we're like islanders adrift in an archipelago, separated by such vast stretches of time and space that signals inevitably fade into noise. There's even the possibility that advanced civilizations transcend physical forms, uploading their consciousness into quantum substrates or dark matter, leaving no trace we'd recognize. What makes the Fermi Paradox so compelling isn't just the unanswered question, it's how it forces us to confront our assumptions about intelligence, technology, and the nature of life itself. Every proposed solution reveals something profound, whether it's the fragility of civilizations or the sheer scale of cosmic time. And while the silence persists, new discoveries keep reshaping the debate. The recent detection of phosphine in Venus's atmosphere, for instance, reminded us that life might thrive in places we've barely considered, or that technosignatures could be hiding in plain sight, disguised as natural phenomena. As we grapple with these ideas, the paradox spills into even stranger territory. If civilizations are rare or silent, what does that say about the laws of physics themselves? Some theorists argue that the universe's constants, the precise strength of gravity, the mass of an electron, might be fine-tuned to allow life, but only just barely. Even a slight shift could render complex chemistry impossible. This rare Earth interpretation suggests we're not just alone in our galaxy, but potentially in the entire observable universe, a statistical fluke in an otherwise sterile cosmos. Yet for all its existential weight, the Fermi Paradox isn't a dead end. It's an invitation to look deeper, to question not just where others are, but what otherness might even mean. As our telescopes grow more powerful and our definitions of life expand, the great silence may yet break, or we might discover that the universe's most profound mysteries aren't about who's out there, but why we're here at all. And with that, we turn to phenomena that defy even the most fundamental laws of physics, where the universe itself seems to rewrite the rules as it goes. If black holes are the universe's ultimate one-way streets, then white holes might be their bizarre, time-reversed counterparts, cosmic exits where nothing can enter, only explode outward. Theoretical physicist Carlo Rovelli's work in quantum gravity paints these hypothetical objects as black holes' mirror images, regions where matter and energy erupt violently into the universe after being crushed beyond recognition in a black hole's depths. Picture a cosmic volcano, endlessly spewing light and particles that once vanished beyond the event horizon, now reborn in a fiery renaissance. The math behind this idea emerges from loop quantum gravity, which suggests that at the tiniest scales, space-time isn't smooth but granular, like a fabric woven from microscopic threads. When a black hole's crushing gravity reaches its limit, this fabric might bounce back, transforming the singularity into a white hole's explosive birth. Rovelli describes the process as a star's second act, where the curtain falls on collapse only to rise again on creation. Unlike black holes, which trap everything, white holes would repel all matter and energy with equal ferocity. Their event horizons would act like impenetrable shields, deflecting even light. The catch, no one's ever observed one. Some theorists argue that white holes could be hiding in plain sight, masquerading as gamma-ray bursts or fast radio bursts, those fleeting, high-energy flashes that puzzle astronomers. Others speculate they might exist only in the distant future, taking trillions of years to form as black holes slowly evaporate through Hawking radiation. The distinction between white holes and wormholes is crucial and often confused. While wormholes are theorized bridges connecting distant points in spacetime, white holes are more like cosmic ejector seats, flinging material out but offering no return trip. Rovelli's models suggest that if a black hole's interior transitions into a white hole, it wouldn't create a tunnel to another place or time, just a delayed and spectacular release of all it had consumed. This transforms the traditional view of black holes as eternal prisons into something more cyclical, where destruction and rebirth are two phases of the same process. Yet the wildest implication isn't just about stellar recycling. If white holes exist, they might rewrite our understanding of the Big Bang itself. Some cosmologists, like Rovelli's collaborator Hal Haggard, propose that our universe's fiery birth could have been the explosive finale of a white hole in a parent cosmos. It's a dizzying thought that every star, planet, and galaxy might owe its existence to the death throes of another universe's collapsed singularity. For now, white holes remain tantalizing ghosts in the equations, waiting for observational proof. But their very possibility forces us to reconsider the universe's most extreme environments, not as endpoints, but as waypoints in a far grander cycle. And if the cosmos truly operates this way, the next tale will stretch that idea even further, bending the fabric of reality into tunnels that could just maybe connect worlds. The black hole gargantua from Interstellar wasn't just cinematic spectacle, it was a painstakingly accurate visualization of a wormhole, crafted with equations provided by physicist Kip Thorne. Those mesmerizing light rings bending around the spherical void, that's exactly how spacetime would warp near a theoretical Einstein-Rosen bridge, a tunnel through the cosmic fabric connecting distant points in the universe. Thorne's calculations revealed something startling. For a wormhole to stay open long enough to traverse, it would need walls lined with exotic matter, a substance with negative energy that defies gravity's crushing pull. The problem, no such material has ever been observed, yet quantum physics hints at tantalizing possibilities. In the subatomic realm, particles can become entangled, instantaneously influencing each other across vast distances, a phenomenon Einstein famously called spooky action at a distance. Some theorists, like Leonard Susskind, propose that entanglement might forge microscopic wormholes, threading space with hidden connections. Imagine two black holes entangled at birth. Their interiors could be linked by a quantum bridge, a shortcut through spacetime's folds. While these tunnels would be far too tiny for human travel, their existence would blur the line between gravity and quantum mechanics, suggesting the universe is far more interconnected than it appears. But here's the catch. Even if traversable wormholes exist, they'd likely be catastrophically unstable. Step inside, and the slightest disturbance, a single photon, could trigger a collapse, snapping the tunnel shut like a cosmic mousetrap. Princeton physicist John Wheeler once compared wormholes to foam bubbles on the ocean of spacetime, constantly forming and popping at scales trillions of times smaller than an atom. Stabilizing one would require engineering beyond anything we can conceive, manipulating dimensions we haven't even discovered yet. Yet the most profound implication of wormholes isn't interstellar travel, it's time. Just as black holes slow time near their event horizons, a wormhole's twisted geometry could link not just places but eras. One mouth might age normally while the other drifts into the future, creating a gateway between centuries. This raises paradoxes that make physicists shudder. What if you traveled back and prevented your own birth? The universe might resolve such contradictions through quantum effects, erasing inconsistencies like a cosmic editor. Or, as Hawking quipped, nature might simply forbid time travel outright with some yet unknown law. These puzzles lead us to an even deeper mystery. If wormholes can stitch space and time together, could they have played a role in the universe's birth? Some models of the Big Bang suggest nascent spacetime was riddled with quantum tunnels, a frothing sea of microscopic bridges that briefly linked disconnected regions before snapping apart. A handful might have survived, stretched and inflated by cosmic expansion into macroscopic structures. If so, the universe could still be threaded with primordial wormholes, hidden relics of its explosive infancy. From the silver screen to the frontiers of theoretical physics, wormholes captivate because they promise answers to our biggest questions about connection, about time, about the universe's very architecture. Yet for all their allure, they remain ghosts in the equations, reminders of how much we still don't understand. And as we peer back toward the dawn of space-time, another enigma awaits, one where the laws of physics themselves may have flickered into existence. For nearly a century, the Big Bang has stood as cosmology's defining origin story, a singular explosion birthing time, space, and matter from an infinitely dense point. But what if that singularity was never the beginning, just one turn in an endless cosmic cycle? Enter the conformal cyclic cosmology model, championed by Nobel laureate Sir Roger Penrose, which paints a far grander picture, a universe where each Big Bang is both an end and a rebirth. At the heart of this radical idea are Hawking points, faint imprints in the cosmic microwave background that Penrose believes are the evaporated remnants of supermassive black holes from a previous universe. These ghostly swirls of radiation, he argues, are cosmic fingerprints, evidence that our universe is merely the latest chapter in an infinite sequence. The math behind this vision is as elegant as it is mind-bending. In Penrose's model, when a universe expands to near nothingness, its black holes evaporated, its particles decayed to pure energy, the distinction between infinite and infinitesimal vanishes. Space becomes timeless and smooth, resetting the stage for a new Big Bang without the need for a singularity. It's a cosmic phoenix cycle where death and rebirth blur into one. As Penrose puts it, quote, "The universe forgets its own scale. What was once vast becomes the seed of the next." This cyclical nature solves one of the Big Bang's greatest puzzles: why the early universe was so perfectly tuned for complexity, with its unnervingly precise entropy levels. If our cosmos inherited its order from a prior universe's demise, the mystery of fine-tuning transforms into a natural consequence of cosmic recycling. Yet conformal cosmology isn't alone in challenging the singularity. The ekpyrotic model, inspired by string theory, proposes our universe arose from a collision between four-dimensional membranes in a higher dimensional space. an event requiring no infinite densities, just kinetic energy on an unimaginable scale. Picture two sheets of spacetime brushing against each other in the dark, their contact unleashing the heat and light we now call the Big Bang. Unlike Penrose's endless cycles, this brain collision scenario suggests a multiverse where universes bubble up like droplets in a boiling pot, each with its own unique physics. What unites these theories is their rejection of a true beginning, offering instead a cosmos without edges, a tapestry woven from endless transformations. But if the universe cycles eternally, what becomes of time itself? In Penrose's framework, the distant future and the remote past become mathematically indistinguishable, a state he calls conformal invariance. Black holes evaporate, particles lose mass, and eventually only photons remain, their wavelengths stretched so thin that the universe effectively forgets its own size. At this point, the cycle resets and time, in any meaningful sense, ceases to exist before beginning anew. It's a concept that bends intuition, not a linear timeline, but a Möbius strip of existence, where each turn carries the echoes of what came before. These ideas force us to confront the ultimate fate of our cosmos with fresh eyes. Will the universe end in heat death, as entropy saps all energy, or will it collapse back into a singularity, only to rebound? The answer may lie in the very anomalies Penrose studies, those disputed Hawking points, some as wide as 8 times the moon's diameter in the sky, could be the Rosetta Stone of cosmic history. If confirmed, they'd rewrite not just our origin story, but our destiny. For now, they remain tantalizing shadows on the map of creation, whispers from a time before time. And as we peer deeper into the cosmic background, we're left wondering, if the universe truly forgets nothing, what other secrets might it be waiting to reveal? The universe isn't just expanding, it's accelerating, racing toward a fate so violent it could shred reality itself. This is the Big Rip, a scenario where dark energy, the mysterious force pushing galaxies apart, grows so dominant that it overpowers every binding force in nature. Picture a cosmic tug of war where the rope isn't just slipping, it's disintegrating. First, galaxies would be torn from one another, their gravitational bonds snapping like overstretched rubber bands. Next, stars would be ripped from their orbits, planets wrenched apart, and finally, even atoms themselves would be split into quarks as space-time fractures at the seams. Theoretical physicist Brian Greene paints this as the universe's ultimate act of self-destruction, where the very fabric of existence unravels in a cascade of unstoppable expansion. But the Big Rip isn't the only possible finale on cosmology's grim menu. Contrast it with the heat death, a slow fade into darkness where the universe exhausts all usable energy, leaving behind a lifeless void of scattered particles too distant to ever interact again. Or consider the Big Crunch, a dramatic collapse where gravity finally wins, pulling everything back into a singularity, a cosmic reset button. Greene frames these competing visions as different chapters of the same story, each revealing how the balance between dark energy, matter, and gravity will determine whether the universe ends with a bang, a whimper, or a tear. What's haunting about these theories isn't just their scale, it's how they reflect humanity's own struggles to make sense of impermanence. Ancient myths spoke of floods and fires cleansing the world. Modern cosmology replaces those with entropy and expansion, yet the existential questions remain. Are we part of a cycle like Penrose's conformal universes, or a one-way journey toward dissolution? The irony is palpable. We've mapped the cosmic microwave background and probed quantum foam, yet the universe's ultimate fate hinges on forces we can't even see. Perhaps that's why these apocalyptic visions captivate us. They're not just scientific models, they're mirrors. In the Big Rip, we see our fear of fragmentation. In heat death, our dread of oblivion. In the Crunch, a glimmer of rebirth. The cosmos, in all its grandeur, becomes a canvas for human imagination, where equations and mythology collide. And as we stare into the abyss of these possibilities, we're left with something profoundly human, the need to find meaning, even in the universe's final act. Now consider this: if the cosmos is racing toward an inevitable end, what does that mean for the stories we tell, the constellations we've named, the civilizations we've built? The answer might lie not in the universe's death, but in how we choose to live within its fleeting, fiery span. Long before telescopes and star charts, ancient cultures mapped the heavens with nothing but naked eyes and storytelling. The Babylonians, meticulously recording celestial movements on clay tablets over 3,000 years ago, didn't just see Orion's belt as 3 random stars. They called it the Shepherd of Anu, a divine marker tied to their agricultural calendar. These early astronomers noticed something profound. The stars weren't just decorations, they were a cosmic clockwork, with Orion's rising heralding the autumn harvest. Fast forward to modern sky surveys, and their observations hold up with eerie precision. The same trio of stars, Alnitak, Alnilam, and Mintaka, that guided Babylonian priests, now serve as anchor points for astronomers measuring stellar distances, proving humanity's celestial curiosity spans millennia. But the Babylonians weren't alone in weaving science into myth. Indigenous cultures worldwide embedded advanced astronomy into oral traditions, often with startling accuracy. The Maya predicted eclipses down to the hour using Venus's cycles, while Aboriginal Australians mapped the Emu in the dark, a constellation not of stars, but of the dust lanes in the Milky Way, its posture shifting with the seasons to signal when to gather emu eggs. These weren't just stories, they were sophisticated observational records, passed down through generations without a single written word. When a total eclipse blotted out the sun over Wyoming in 2017, Lakota elders weren't surprised. Their ancestors had described the sun's temporary death centuries before Western science calculated its path. What unites these ancient skywatchers with modern astrophysics is a shared truth. The cosmos speaks in patterns, and humanity has always listened. From Babylonian clay tablets to the Hubble's deep field images, we're piecing together the same puzzle, one where myth and math aren't rivals, but different dialects of discovery. The constellations Orion tracked for omens are now laboratories for studying stellar nurseries, proving that curiosity transcends time. As we stand on the shoulders of these stargazing giants, their legacy whispers a final, unifying lesson. Whether charting eclipses with stone circles or black holes with quantum equations, we're all part of the same endless quest to decode the universe's grand story, one observation at a time. And in that shared journey across cultures and centuries lies the real wonder. The night sky doesn't just belong to astronomers. It's humanity's oldest heirloom, a mirror reflecting our timeless hunger to understand where and why we fit in the stars. From the infinite blackness of space, Earth is not just a planet, it's a shimmering oasis, a fragile blue marble suspended in the void. Astronauts who have witnessed this view first and describe something profound: the overview effect, a cognitive shift that shatters borders and divisions, revealing our shared home in its true vulnerability. Chris Hadfield, during his time aboard the International Space Station, captured this revelation perfectly. You look down and realize you've been lied to your whole life. There are no lines marking countries, just this one breathtaking planet we all share. It's a perspective that transforms not just how we see Earth, but how we see ourselves, not as citizens of nations, but as crewmates on spaceship Earth. This shift isn't just poetic, it's scientific. studies of astronauts' psychological responses show consistent patterns, a deepened sense of connection, an urgency to protect the planet, and a humbling awareness of humanity's smallness in the cosmos. When you watch hurricanes swirl over continents without regard for political boundaries, or see the paper-thin glow of our atmosphere, the only thing shielding us from the vacuum, it rewires your priorities. Astronaut Nicole Stott, after her spaceflight, founded the Space for Art Foundation, blending space imagery with children's art to inspire global environmental stewardship. From up there, climate change isn't a debate, she says. You see the deforestation, the shrinking ice caps. It's like watching your house catch fire in slow motion. The overview effect's power lies in its universality. Ancient astronomers mapping the stars and modern astronauts gazing back at Earth are united by the same awe, a recognition that curiosity and exploration bind us across time. When the Apollo 8 crew read Genesis while orbiting the moon on Christmas Eve, or when Sultan Al Nayadi, the UAE's first long-duration astronaut, shared Quranic verses about the cosmos from the space station, the message was the same: the cosmos dissolves barriers. It's no coincidence that the first photograph of Earth from the moon, Earthrise, became a symbol for the environmental movement. That single image, showing our planet as a lonely, glowing jewel, sparked a global realization: we're all in this together. This cosmic perspective doesn't just inspire unity, it fuels discovery. The same wonder that drives us to protect Earth propels us to explore beyond it. Mars rovers, deep space telescopes, and plans for lunar bases aren't just scientific endeavors, they're extensions of our innate need to understand our place in the universe. Astronaut Mae Jemison, the first black woman in space, frames it as a cycle. Exploring space teaches us about Earth, and understanding Earth pushes us back into space. It's a feedback loop of curiosity and care where every new discovery, whether it's water on Mars or microplastics in our oceans, reminds us how precious and rare life truly is. So what do we do with this perspective? The overview effect isn't just for astronauts. Through images, storytelling, and the democratization of space via private missions, more people than ever can experience a version of this shift. Start by stepping outside on a clear night and looking up. That's the same sky Galileo studied, the same moon that guided ancient navigators, the same cosmos that humbles and connects us. Then look around at the people, the trees, the air we all breathe. The universe has given us two gifts: the ability to explore its vastness and the responsibility to protect our tiny corner of it. The next chapter of our story isn't just about reaching new worlds. It's about cherishing this one while daring to dream beyond it. And that's the true lesson of these 25 celestial wonders. They're not just distant curiosities, they're mirrors, reflecting back our courage, our creativity, and our capacity to change. From the birth of stars to the edge of black holes, the universe whispers a simple truth: we are stardust, awake and wondering. So let's keep looking up, asking questions, and reaching further, because the greatest discovery isn't out there in the cosmos. It's what the cosmos reveals in us. From the eerie silence of the Boötes Void to the violent ballet of colliding galaxies, these 25 cosmic wonders reveal an undeniable truth. The universe is not just stranger than we imagine, but stranger than we can imagine. Every discovery peels back another layer, only to expose deeper mysteries waiting beneath. Consider Tabby's star, flickering like a cosmic Morse code we can't decipher, or the Great Attractor, pulling thousands of galaxies toward some unseen destiny. Even our own solar system hides secrets, from Planet 9's phantom gravity to the rogue black holes that might lurk in the darkness. These aren't just puzzles for astronomers, They're invitations to wonder, to question, to look up and realize how much we've yet to learn. Carl Sagan once reflected on the iconic pale blue dot image, Earth as a speck in Voyager's distant lens. Look again at that dot, that's here, that's home. In a cosmos of black holes and diamond planets, our world is both impossibly fragile and extraordinary. The same forces that sculpted the pillars of creation shaped the atoms in your hands. The same dark flow tugging at galaxies' courses through the space between us. This connection isn't poetic license, it's physics. Every time you gaze at the stars, you're witnessing the same light that guided ancient navigators and inspired Galileo's telescope. The universe doesn't belong to scientists, it belongs to everyone curious enough to engage with it. So what's next? The answer lies in your own sense of wonder. Maybe it's stepping outside tonight to trace Orion's belt, or joining a citizen science project to classify distant galaxies. Perhaps it's simply sharing these stories with someone who's never heard of the great cosmic silence or the phantom pull of dark flow. Science isn't a closed book, it's a conversation, and every new voice, whether a child with a backyard telescope or a researcher analyzing quantum foam, adds to the collective quest. As we close this journey, let's return to Sagan's words, more urgent now than ever. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. In a universe of vanishing stars and colliding dimensions, Earth is our only home for now. Cherish it, protect it, and never stop exploring. The cosmos awaits. If one of these 25 tales sparked your curiosity, let us know in the comments. Was it the diamond planet, the runaway black hole, the whispers of parallel universes? Hit like if you're leaving with more questions than answers, and subscribe for more deep dives into the mysteries that make our universe so breathtaking. Until next time, keep looking up. The next great discovery might begin with